Welcome to the session. So the previous session we have discussed about how the assembler can assign the address to each instructions in the program we have discussed. So we'll move on to the next step by the assembler, how it generates the object code. Well, generating the object code, the assembler will be identifying the instruction format and addressing mode based on which it is creating the object code. Now, let us take the example, the line number 10, STL-RET-ADR. So as you already knew that the STL, which has the value, the machine equivalent is 14. And RET-ADR is a symbol, so for which the TA has to be calculated. The TA is nothing but the address of the target. So the RET-ADR, which is stored in the location 0030, which I have already told you. If you could see the program example, in the line number 95, RET-ADR is defined. So the TA is nothing but 0030. So this is the TA, is the address for the symbol RET-ADR. Now, if you look at the instruction format, as you could see, this instruction format is based on the format 3. In format 3, we have the opcode which takes 6 bits and followed by the NIXPP bits, followed by the displacement 12 bits. Now, the opcode, as we knew already, the STL is having the value 14. So the value 14 has to be accommodated in the opcode. So opcode has only 6 bits. So the first 4 bits will be representing the first digit for the STL, and the another 2 bits will be representing the second digit of the STL value. So first 4 bits will be forming 1, that is 0001, which is representing 1, and the second 2 bits, this another 2 bits out of the 6 bits, that will be 01. So why 01? Because it will be representing 4, right? If you take the 8421 format, so 84 will be there in the 2 bits of 6 bits. So in the place of 4, we have 1. So it is representing obviously 4. So if you could see the 6-bit, that is opcode, 0001, which represent 1, 01, which represent 4. Now, the format 3, I have already told you that format 3, which is a relative addressing, and it is a simple addressing. When it is a simple addressing, in format 3, N and I bits are 1, as we have already seen in the example. I have shown you some example where there was a calculation for TA in which the N and I bits were 1. When the N and I bits were 1, I was telling you that it is a simple addressing. So it is a simple addressing, and E bit will be 0 as it is following format 3. So the difference between format 3 and format 4 will be decided based on the E bit. So since it is a format 3, we follow the format 3, E bit is 0. And coming to the B and P bits, whenever we use the indexed addressing, the base register also will be used. So except those instructions, all the remaining instruction uses the program counter. If it is following program counter relative addressing mode, obviously P bit will be 1 and B will be 0. Now, the next place would be for the displacement. Now, how do we find the displacement? As you could see in the previous sessions, I was telling you that if it is an SACXC, And if the relative addressing is PC relative, then the calculation for TA is based on the formula which I have given you in the previous sessions, where I have shown you the formula for calculating TA if the address is of the type program counter. So what is the formula for TA? TA is equal to PC plus displacement. PC plus displacement. I'll just go back to the slide so that I can show you the formula to calculate the TA. So which is there in the SAC XC format what we have discussed previously. So this is what the formula says. If it is the base relative, TA is equal to base plus displacement. If it is a program counter, TA is equal to PC plus displacement. In that case, B and P bits, B is 0 and P will be 1. So this is what we have discussed previously when we were discussing about the SACXC. So the same thing which we use now to find out the displacement. Why I'm telling the displacement is because we know the value of PC. How do we know the value of PC is? See, when you are in the line number 10, as you know, what is the address of line number 10 is nothing but 0, 0, 0, 0. And you know that the instruction format of the line number 10 is format 3. So obviously it takes 3 bytes. So you can identify the PC. PC is nothing but address of the next instruction. So here, what is the address of the next instruction? 0, 0, 0, 0 plus 3, nothing but 0, 0, 0, 3. So 0, 0, 0, 3 is the PC value. And you know that what is the value of TA. So as I have already told you that RET-ADR, so that is the symbol. We should know the address of the RET-ADR, which already I have shown you in the line number 95, 0030. So now in the formula, that is TA equal to PC plus displacement. In this formula, we know the value of TA and we know the value of PC. Now, we have to know the value of displacement. So, how do we get the displacement? So, displacement equal to TA minus PC. So, TA is 0030 minus 0003. That is the PC value. When you subtract, do the subtraction, you will be getting the value as 002D. This is your displacement. So herein we have 4-digit number, that is 002D, out of which we take only the 3 digits from the right, as the displacement has only 12 bits. The preceding zeros we leave it. So we take only the last 3 bits. That's nothing but 0, 2D. Now, if you look at this instruction format in the slide, in place of the displacement, we keep the value 0, 2D. How the 0, 2D is represented using binary format, which is shown in the slide. So in the displacement field, the 0, 2D is represented as 0 is represented as 4 zeros and 2 is represented as 0010 and D is represented as 1101. Now if you look at the entire instruction format, from the starting, all these are represented in the binary format. So we make in the hexadecimal format. So now if you look at starting from the opcode, so in the opcode, you take the first 4 bits, 0, 0, 0, 1. So that will be forming the value as 1. Then next 4 bits. So 2 bits from the opcode and 2 bits from the N and I. So this will be forming 0, 1, 1, 1. It's nothing but 7. Then we have X, B, P, E bits. So this is actually 0, 0, 1, 0. It is forming the value 2. The remaining displacement field 0, 2D. So if you look at the object code 17202D. This is the object code for the line number 10. This is the object code for the line number 10. This is the way how the assembler derives the object code for that particular line. Similar fashion, we can understand the remaining instructions also will be converted into object code by the assembler. So when any instruction is taken by the assembler, so the assembler will interpret what is the instruction, which instruction format it is following, which addressing mode it is considering, and based on which it creates the object code. For each and every line, the object code is generated except the pseudo instructions. The pseudo instructions are nothing but the instruction which cannot be translated into the object code. Only these instructions are useful for the assembler to provide some information. It's maybe with respect to storage. So here you can see the instruction format. So from the instruction format, that object code is accommodated inside the instruction format. The same thing which we have done in the SIC machine also. Similar to that, we have so many other examples too. So if you look at this slide, which gives you an overall idea about what are the different addressing mode. So when you see the instruction, we can easily make out, so this particular instruction is following which kind of addressing mode. Say for example, if you consider the opcode followed by memory, then it can be a PC relative or base relative. That is the one example we have seen. And if the instruction has opcode followed by @ symbol and followed by the memory address, then it is representing indirect addressing. So whenever you see @ symbol, it is representing indirect addressing. And hash symbol followed by C, nothing but constant. So opcode hash C, that is an immediate addressing. And which opcode with the plus symbol, which represent the extended format. And opcode followed by memory, comma X, that is following the index addressing. And apart from that, we have only the register to register instructions. So the purpose of having SICX is which has the larger memory. Because of the larger memory, so there are possibilities of multi-programming. So more than one program can run, and also it will be very faster since we use only the register to register instruction in some places, not all. In few instructions or some instructions, we use only the registers, make use of the registers without referring any memory. Because of this, it will be faster. It leads to faster execution. So when you have the registers, as we knew already, we have seen in the beginning of the sessions, in the previous sessions, wherein each and every register has the corresponding numbers. Say for example, A register which is represented by 0, X register 1, and so on. So these informations will be stored in the symbol table. Okay, so when you are referring the registers, instead of referring the registers names, you can refer by means of the numbers also. And this information, format 3, what is the value of base register and what is the value of PC, we have already discussed. So here are some more examples for the PC relative addressing mode, how the object code is generated out of this. So if you look at the line number 10, that is what already we have seen, how exactly the object code is generated, and it is represented in the instruction format. And taking the line number 40, so here in the line number 40, we have the instruction J C loop. Okay, and as you could see, this is same as the previous example. So it has to follow the instruction format 3, and if it is an instruction format 3, then it is a relative addressing. If it is a relative addressing, and since it is not using any index register, so it follows the PC relative addressing mode. And if it is a PC relative addressing mode, the TI calculation would be PC plus displacement. And as usual, the PC value and TA value we will be knowing. So we are supposed to calculate the displacement part. So during the calculation of displacement, so in order to calculate the displacement, we should know what is the value of TA and what is the value of PC. So the line number 40, we have the instruction, and the symbol is C loop. So we should understand what is the value of C loop and what is the value of the PC value. So just I am going back to the program so that you can see what is the value of C loop and what is the value of PC. So the line number 40, this is the example we have taken to consider for the object code. Why this example is taken is there is little deviation we can find from this particular example than compared with the previous one, the line number 10. If you look at this instruction J C loop, so C loop is a symbol, so which is in the location 15, line number 15, in the location 0006. So 0006 is the target address. Since the symbol is C loop and which is defined in the location 0006, that is the target address. And we are referring the instruction line, the line number 40. So what is the address of the next instruction? It is 001A, which is in the line number 45. So obviously the PC value is 001A. So you know that the TA is 0006 and the PC value is 001A. So now coming back to the calculation part. So as we know, TA minus PC, that gives the displacement. So when you subtract 0006 with the 001A, so obviously the negative value will be bigger one here. So from the negative number we have to do the subtraction. So when the negative number is bigger one, obviously the result will be in the negative number. That's why when you subtract 1A minus 6, so A is 10, so 10 minus 6 is 4, so 1 will be as it is. So 14 is the value, but it is in the negative number. Since it is in the negative number, so I have already told you that the SEC supports floating point and it's supporting integers and character also. When you deal with the integers, it can accept the negative values. If it is a negative value, then it has to follow the 2's complement representation. So when you make the 2's complement for this particular number, first of all, you have to make the 1's complement, and then it has to be 1 has to be added with the 1's complement to get the 2's complement. So this is a procedure. So what is the displacement here is minus 0, 1, 4. This is the displacement. So for the 0, 1, 4, we have to get the 2's complement value. Since it is a negative number, we have to get the 2's complement value. That is what exactly FEC. How to get this FEC is 0, 1, 4. You have to mention in the binary format, and that binary forms should be converted into 1's complement. Then with the 1's complement, you have to add 1 so that you will be getting the 2's complement. So when you do this calculation, you will be getting the value as FEC. This is your displacement. The rest will be same. When you find the displacement, the remaining all these things will be you can identify the same way the remaining all. So herein we have the values over here. So when you take these values, opcode and NX BP bits, so same way whatever the way we have to do, the same way we can do it here also. Now if you look at the opcode, we have to know the value of the J. Okay, so the value of J is 3C. So 3 is mentioned with 0011 and C is mentioned with 11 because that will be holding the value of 8 and 4. So it's 12, 12 is nothing but C. So J is represented by 3C. Then, since it is a format 3 and simple addressing, N and I became 1 and 1. And X bit is 0 since we don't use X register. Then B and P, since we follow the PC relative, 0 and 1. And since it is a format 3, E bit will be 0. And FEC will be the displacement. So when you combine all these things, you will be getting the object code as 3F2FEC. So each 4 bits will be forming 1 digits in the object code. So that is how first 4 will be forming 3. The second 4 will be forming F. The third 4 will be forming 2. And finally we have the displacement that is FEC. So this is the way how we exactly derive the object code for this particular instruction. So these both instructions are same. Both are following the PC relative. The only the difference is when the displacement is derived, the displacement can have the negative value also. So when there is a negative sign in the displacement, then it has to be converted into 2's complement. It has to be represented in the 2's complement format. So that is the reason. So the two different way of calculating the displacement is given as an example. So this is the example for PC relative. So based on these calculations, the same way the other instructions also will be used for PC relative. And coming to the base relative, if there is a base relative, so you can see the line number 160, wherein you can find the X register, so which follows the base relative, and we have the TA, it's nothing but the buffer. Target address, that is the address of the buffer is nothing but the TA. Okay, so similar fashion like PC relative, base relative also will be calculated. Only the difference is instead of PC here, the assembler uses the base relative addressing. Okay, so in the base relative addressing, what is the value of base relative base register? So that is actually given by the line number 13. So as I was explaining about the instructions, that time I have told the base is the assembly directive which is used to assign the value to the base register. So herein the base register values nothing but the value of the length, where the length is define, that address will be the base register address. So B will be having the value 0033. That is the base value. And we should know the value of buffer. So what is the address of buffer or where it is defined, that address we should know. So we follow the same formula like TA is equal to B plus displacement. So in the previous case we have used BC plus displacement. In this case we will be using base plus displacement. And as we could see, the B value we can understand, and T value we can get to know. Then the thing is, the displacement has to be derived. So to derive the displacement, again TA minus B, base register. So what is the value of TA? We should get it from the program. So if you could see the program, buffer is defined in the location 105, in the line number 105. The location is 0036. This is the target address. So when the buffer is defined in the location, that is the target address of the buffer. So this value we consider as a TA, and we have the base register. So base register in the line number 13, if you could see in the program also, the line number 13, base length. So where the length is defined in the line number 100. So in the 100th line, you could see the definition of length which is there in the location 0033. So 0033 is the value for the base register. So you know the value for base register, you know the value of TA, then it is easy to find the value of displacements. That's what exactly happening here in the this line. Displacement is equal to buffer minus B, that is TA minus B register. So TA is 0036 minus 0033, that is giving the value 3. So 003 is the displacement. And if you could make out the values in the instruction format. So since it is the format 3, we can have the opcodes over here. So the opcode, which is nothing but 54 for STCH. So we have the 54 value for STCH, that is represented as 5 is mentioned as 0101 and 4 is mentioned as 01. And it is a simple addressing, even though it is a base relative. So since it is a relative addressing, simple addressing, n and I will become 1. And you can see the instruction. There is a X register. So X register is meant for indexing purpose. So the X bit will be 1. And since we use the base relative addressing mode, B is 1 and P is 0. And since it is a format 3, E bit is 0. So in the displacement field, we have the value 003. So when you form the first 4 will be forming 5. The second 4 bits will be forming 7. The third 4 bits will be forming C. Then we have 003. This is the way how the object code is derived from the base relative addressing. So the base assembler directive is used to assign the value for the base register, whereas when you use no base in your program, it is used to inform the assembler that it is not all going to be used. So the content of the base register is no longer be used for the addressing purpose. That is the purpose of the no base, whereas when you use base, it represents the base register is assigned with the value. The next example would be immediate addressing. So in this particular thing, immediate addressing, there are two cases we can see, LD A #3 and LDT hash 4096. Okay, so in these two cases, we are using the immediate addressing with the constant. So the constant 3 and constant 4096 is being used. So in these two cases, you can make out the difference between these two instructions. One is actually following the format 3 and other one is following the format 4. The reason behind this, in the line number 133, the instruction follows format 4, whereas in the line number 55, the instruction follows format 3. So since we have the plus symbol in line number 133, it is following the format 4. So now if you consider the first case in the line number 55, so LDA hash 3. For LDA, the value is 0, 0. So the LDA, the value is 0, 0. So in the opcode field, you can see that 0, 0, 0, 0 for 0 and 0, 0 for another 0. And one thing you have to notice here, when you represent N and I, so even though it is a format 3, since we use the hash symbol, it follows immediate addressing. So what happens to the N and I? So the both will not become 1. Instead, N is 0 and I is 1 because it is following the immediate addressing. When it is following immediate addressing, I will be 1 and N will be 0. And there is no indexing. So X is 0 and it is not following the relative addressing. So B and P will be 0, and since it is a format 3, the E will be 0. And in the displacement, we don't do any calculation. We are not able to see any calculation over here because since it is an immediate addressing, it is taking the same operand value as displacement. That is why the value 3, which is represented as 0, 0, 3. What is the constant we use in the instruction? Same constant we use here also, only the preceding zeros are used because it won't change any value. So if you look at the object code, the first 4 bits will be 0, the second 4 bits will be forming 1, then third 4 bits will be forming 0, then the remaining 0, 0, 3 is the object code. The displacement, then the whole thing is the object code. And coming to the second instruction, in the second instruction, we have LDT hash 4096. Now the LDT values mentioned here, we have 0, 1, 1, 1. So this format will be having, so 0, 1, 1, 1, that will be nothing but 7. And we have 0, 1, that's nothing but 4. So 74 is your LDT value. And again, N and I will become 0, 1, 1, X is 0, then B and P will be 0. Now there is a change in E bit. So compared with the previous instruction and this instruction, since that was following format 3, E bit is 0, whereas here E bit is 1 because it follows format 4. And if you see the address field, so since it is a format 4, in the address field we have 20 bits instead of 12 bits, we have 20 bits. That is the reason the 4096, which is represented as 01000. Why instead of 4096,000 is, I already told you that the maximum limit is 1000. So when the number of bytes which is assigned for the reserved for the buffer, it is taking only the 1000 bytes. That is the reason it is taking only 1000 value, the constant 1000. So 0, 1, 0, 0, 0. So we have 5 digits because each digit will take 4 bits. So 5 4s are 20 bits. So that will be formed in the address field. So this is the difference between the immediate addressing in format 3 and format 4. This is one of the ways how the immediate addressing is being used. And another way how the immediate addressing is being used is, so here in the same instruction, so according to whatever we have discussed, if you follow that one, then the 12th line would be having the value as similar to the second case. See, actually, the example is same example in the line number 12, same example, that is LVB hash length. But if you see the object code, there is a difference in object code. The first example showing some object code, the second example showing the different object code. You could see that the second example is following as per whatever we have discussed about the immediate addressing. But one thing we have to notice that in the both the cases in the previous example, that was using the constants, whereas here in this particular line, the line number 12, which with the immediate addressing, it uses the symbol. So it is following the PC relative addressing mode. So that is how it is according to the PC relative, it follows. If you look at the NIXBP bits, N bit will be 0 and I bit is 1. It is representing immediate addressing. And if you look at the B and P bits, B is 0 and P is 1, it represents PC relative and E bit is 0. So to find out the displacement, it follows PC relative addressing mode. So TA minus PC, that gives you the displacement. That is what TA is length, that is 0033, and PC that has the value as 006, 0006. So which gives you the value as 02D as a displacement. That is what you can see the displacement field. In the displacement field, 02D is the displacement, and that's how the object code is formed. So when there is a symbol which is used with hash, that is the immediate addressing, then it has to follow according to PC, not as per the constant. That is what the difference which is shown in these two cases. So we have indirect addressing as well. Indirect addressing, whenever there is an instruction in the instruction, when there is a at symbol which follows the indirect addressing. Indirect addressing also follows the PC relative. So in the line number 70, you could see the instruction J at RET ADR. So RET ADR value, already we knew that it is a 0030, and we have the PC value. The address of this 70 line is 002D, and the next instruction would be obviously 002D. Okay, that is the PC value. So we know the target address, we know the PC value, then we can easily find out the displacement. So 0030 minus 002D, that gives you 0003. That is the displacement. So this is how we can get the displacement from this. So in the case of opcode, so again the same will be followed. The 4 bits and 2 bits, and n bit will be 1. Since it is the indirect addressing, n bit will become 1, and I bit will be 0. Then x is 0, b is 0, p bit will be 1, and e bit will be 0. And the displacement is 003. This is how the conversion is taking place over here in the case of indirect addressing. And some more instructions can be converted into object code, which follows the different instruction formats. So in those cases, how exactly the conversion is taking place and what would be the object code which is created by the assembler, that we'll see in the next session. So we'll end up this session.